Hi everybody, my name is Ryan. I'm one of the educators here at the Headwaters Science Center, and it is 3:30, which means it is time for one of our after-school STEM shows. And what we've been doing for the last couple days is talking about some of the exhibits that we have down on the exhibit floor, kind of giving you a little bit of a more in-depth look at them than what you might get if you just came and looked at them yourself. And, and so, today we're going to be looking at one of our longest running exhibits that we have here, one that's been here pretty much since we opened, and that is the pitching cage, one of our most popular exhibits, but one that I feel like a lot of people probably don't often get the full experience of because there's a lot of really complicated ideas happening here that might not necessarily be apparent right away when you look at it. And so, I guess just getting into the basics of what this is we have how you would come and interact with this, at least right now during COVID, is that we have wiffle balls for it, and generally we would keep the wiffle balls right in the cage here, but right now we're keeping them behind the front desk. So if you come here and you want to visit and experience the pitching cage, what you'd have to do is you'd have to go to the front desk, ask whoever is there for a ball for it, and they would provide you with one of these wiffle balls. So I've grabbed two here. And then basically the way it works, and if you want to angle the camera up here to catch that, you take the ball, you throw it at the target, and it tells you how fast you threw it. And so it seems like a pretty simple concept until you start getting into, well, how does that number know how fast it was that I threw that ball? And it's using some pretty high level, pretty complicated physics to get that across. And so if you see, there's a little box up here, and inside that box is a radar gun. And so what radar is how a radar gun works is it kind of shoots out these waves all the time, and when you throw the ball, it is shooting those electromagnetic waves out, and it bounces off the ball, it bounces back into the receiver on the gun, and based on what we call color shifting of those waves, it knows how fast your ball is moving. And so this is all stuff that's happening on a extremely fast pace, is happening way faster and in way more fine scale than what the human eye can pick up. But like I said, it relies on this idea called color shifting. And so you'll oftentimes hear this in terms of sort of the opposite ends of the spectrum. You have red shifting and you have blue shifting. And so this is called the Doppler effect, is when that comes into effect. And so what happens is when you shoot a wave at something that is moving, depending on how that thing is moving, it's going to affect how that wave comes back. And so if something is moving away from the wave and you try and shoot a wave at it and have the wave bounce back, it's going to get stretched out a little bit. It's going to seem, when it comes back, like that wave is a little bit longer than it actually is. Kind of artificially inflates the length of the wave. And vice versa, when something is coming towards you and you shoot a wave at it and that wave bounces back, it's going to seem a little bit tighter, a little bit closer together. And so when stuff is going away from you, we call it red shifting, and when stuff is coming towards you, it blue shifts. And with light, this isn't something that we can ever really perceive with the human eye. It happens on, like I said, such a fine scale that you're never really going to see it with your human eye. But we do have tools that can detect this, and we use these all the time. So like I said, our radar gun up there is a great example of something that is detecting a color shift that we couldn't ever do with our human eye, but it is very capable of using. Detecting color shifts and using the Doppler effect is how, for example, we know that our universe is expanding. So you can do something similar, shoot it up at the sky with a very high-powered microscope and camera, and detect the color shifts of the stars as they are up in the sky, and say, okay, this one's pretty much all the stars around us are red shifted, which means that they are moving away from us, which must mean that our universe is expanding. And so that's how we came up with that idea back in like the 1920s or 30s. That's how we know that the universe is expanding, is through this exact same effect. But here's a fun one, kind of related to that same thing. Every once in a while, we'll encounter a star if we sit there and we look at it and we keep bouncing waves off of it to check the Doppler effect. Every once in a while, you'll encounter a star that red shifts for a little while, and then it blue shifts for a little while, which means it's coming closer to us. Then it red shifts for a little while, and then it blue shifts for a little while. And maybe we can think about it for a little bit here, why that would happen. Why might a thing be coming closer and then getting further away from us out in space. Watch here for a couple seconds, let you all think about it. And in that situation, generally what you're experiencing is a star that is orbiting around something else. And so, more often than not, it's going to be another star. So sometimes you'll get systems where you have two stars orbiting around each other. So when you have two stars orbiting around each other, at a certain point, it's going to be coming closer to Earth. And so it blue shifts when it's coming closer to you, then it red shifts when it's going away. On the whole, they're generally red shifting because they are moving away from us, but there's going to be times where it is actually getting closer to us, and so you see it as a blue shift. And so this is a way that we have actually found a lot of stars that we can't even directly see with a telescope, is by detecting the light that comes from them, which I think is kind of cool. And so the Doppler effect isn't something that is exclusive to light. The Doppler effect affects anything that makes a wave. And so the other obvious thing, and probably the most, the Doppler effect that you're probably most familiar with, that you've encountered the most often, is actually with sound. And so think about when you hear like a ambulance or a police siren. When it's coming towards you, it sounds a certain way, and then as it drives past you and starts going away from you, it sounds different. And what you're experiencing there is the Doppler effect, that same exact effect except applied to sound. And so when it's coming towards you, it is sort of artificially compressing the waves so that the siren will sound higher, and as it's going away, it's artificially stretching out the waves to make it sound lower to your human ear. And that's an example of, like I said, the Doppler effect being applied to sound rather than light. And a couple other places where you'll see the Doppler effect, a couple other uses for it. We use it a ton in weather forecasting. That's more, that tends to be very similar type of Doppler effect to what we're seeing in here, where it's using microwaves. So if you ever are watching the weather report and they talk about their dual Doppler system that they have, the reason it's called a dual Doppler system is just because it's using this exact same stuff. It's using the same technology, just on a bigger scale. The satellite on top of your house, if you have satellite TV, is relying a lot on Doppler effect to tell what kind of signals it's supposed to be putting out there. Doppler effects all around us. We use it a ton for a ton of different things. Anything that uses radar on any level relies on it. But yeah, so the other aspect of this, obviously, is it's not just a laser that you can see, or can't see. It is a kind of a fun experience as far as kinesiology, the way that your body is moving. How do you throw a fast pitch? What's the physics behind throwing a ball accurately and quickly? And so there's some interesting stuff with that too. When I was looking up kind of stuff to talk about with this one of the things I was reading up on was Major League Baseball pitchers. So people who are probably better at throwing a ball of this type of scale than anybody in the world. And one of the things that was really interesting that I was reading about is how tall so many Major League Baseball pitchers are. And that's something I observe here too, is that the people who are able to throw the ball the fastest generally are the tallest. And that makes a lot of sense because, that's basic simple machines. A longer lever is able to generate more leverage than a shorter lever. So if you come here and you're here with a few friends, and maybe you'll notice that the taller folks tend to have a little bit of an advantage when it comes to throwing the ball harder. You can make up the difference if your form is better, or if you're really quick about your acceleration on your throw. But by and large, people who have a longer lever, a longer, particularly forearm, are going to be able to throw the ball a little faster because it's a basic simple machines, basic physics. Longer lever generates more force. It's just the same way as if you got that, you're working on a car and you have that nut that you really can't get off. Just get a wrench with a longer handle on it and it's going to be easier for you. Again, same principles. The other thing that, kind of going back to the machinery we have here, is that radar guns like this are something that you'll see in testing the speed of baseballs, but also when the police are checking for speeding, they use a very similar type of machine as this, a radar gun. Although they're becoming progressively less common, they're kind of being replaced by what are called LiDAR guns. And so LiDAR guns operate very similarly, but they use, rather than sort of a boom of radar or a boom of microwaves to do their thing, instead they rely on a much smaller, much higher frequency laser. And so the big benefit of it is that they are able to focus the laser is much more focused, so it's much more easily targetable. It's much less apt to experience interference from outside things. Like radar guns are notoriously easy to interfere with. Like they'll even pick up like if there's some tall grass nearby that's swaying a little too fast, it can mess up your radar gun reading. And you'll see that even occasionally here at the Science Center. If there's too many people moving around, sometimes it creates some problems for a radar gun to detect a good reading. But LiDAR guns, because they use a much more focused beam and are using a little bit different type of wave, they're a little bit more reliable. They're more expensive, but you're starting to see them largely get replaced. But yeah, kind of a seemingly simple little exhibit that we have here that a lot of people are just going to come up and run up on and throw some balls and have a little competition to see who can throw it the fastest or most accurately, or sometimes the slowest. That's a fun one too. Who can throw the slowest ball and actually get it picked up on the radar. But there's a ton of really interesting physics happening there that hopefully you guys have some understanding of. So I'll say thank you all for watching. If you are looking to come by, the Science Center is open. We are currently open Friday, Saturday, and Monday from 9:30 to 5:30. We are open Sunday from 1 to 5:30. We have some limitations right now because of COVID, so we're requiring all of our guests age 6 and up to wear masks. We're limiting our capacity right now. We're encouraging all our guests to maintain all those social distancing measures. You know, be smart and be safe when you're here, but we would love to see you come in and visit with us. So thank you all for watching.